This video continues the idea of proofs, and we're proving statements about segments and angles in this video. And our examples are going to answer the essential question, how is a geometric proof developed? We'll see not only will we apply some definitions, postulates, and statements that we've come to see, but we'll also use the structure of a proof in our examples to develop these. First example here, we've got a line segment and some given statements. We know that segment EF is equal to segment GH, and we want to prove that segment EG is congruent to segment FH. And we'll start by marking the line segment with the markings indicated by our given information. So EF is the distance EF is equal to the distance GH. What are we trying to prove? We want this segment EG congruent to FH. So how can we prove it? We create two-column proof, statements on the left and the reasoning on the right. The first statement is always going to be the given information. So the measurement of EF is equal to the measurement of GH. That's given. We're going to apply steps along this process to get to the final line of what we want to prove. So if that's true, you can see we add segment FG to both sides of the equation. If you see it right here, what we've done is we've taken our first line and we've added FG on the left side and we've added FG on the right side. Okay, so we're adding to both sides the same quantity. We can do that because of the addition property of equality. Well, now that we've done that, we can take this EF plus FG. So in our diagram, here's segment EF, and we're taking FG, we're adding it together, and that's going to get us our entire distance EG. And if we take this right side of the equation, FG, and add GH, then that gets us this distance FH. And the reason why we can do that is the segment addition postulate. Well, if EG is equal to EF, if their distances are equal, then that must mean that the segments are congruent, and that's by the definition of congruent segments, and we've reached the statement we've been trying to prove. So that's it. That's our two-column proof for this first example. Here's a triangle, and we know that LK is equal to 5. That's the base of this triangle. And we know that JK, the side on the left here, is also equal to 5. Segment JK is congruent to segment JL. And so let's prove that segment LK, the base, is also congruent to JL. So let's start our two-column proof with our given statements. Well, if the two side lengths that we know the lengths of are both 5, then we can say that their segments are equal to each other, and that's by the transitive property. One equals 5 and 5 equals the other. Okay, if their measurements are the same, if their lengths are the same, that must mean that the segments are congruent. That's by the definition of congruent segments. Well, if LK is congruent to JK, and in our given statement we had, so LK is congruent to JK, and in our given statement JK is congruent to JL, then we can put those two statements together and say that segment LK is congruent to segment JL, and that's by the transitive property, and we've proved exactly what we were hoping for. Okay, so 4 steps in that example. Let's take a look at another one here involving the midpoint. So B is the midpoint of segment AC. Segment BC is congruent to segment CD, and we want to prove these red squigglies here that the length of AB is equal to the length of CD. So that's what we're trying to prove. We'll build our two-column proof. Always start out with a given for the first line. B is the midpoint of AC. Well, if B is the midpoint of AC, then that must mean that segment AB is congruent to segment BC. That's the definition of the midpoint. We know that the two segments created with the midpoint are congruent. If those two segments are congruent, rather, we're going to take segment AB congruent to BC, and the given that segment BC is congruent to CD, like we saw in the last example, put those two congruent statements together, and we can conclude that AB is congruent to CD because of the transitive property. We're almost there. The congruence isn't what we're trying to prove. We're trying to prove the measurements are equal. So one more step to say that the measurement of AB, the distance AB, is equal to the distance CD, and that's by the definition of congruent. Congruent segments. Okay, another example here involving the transitive property with measurement of angles. Given this diagram over here, we know that the measurement of angle 3 is 40 degrees, that angle 1 is congruent to angle 2 is congruent to angle 3. That statement alone right there is probably foreshadowing this transitive property. You probably can already see it shaping up, but let's go step by step to create our two-column proof. Always start out with the given statements. Our second step here is to say that angle 1 is congruent to angle 3 by that transitive property that I had alluded to earlier. Knowing the measurement of angle 3 is 40 degrees, well, sorry, I got ahead of myself. The angles are congruent, but now their measurements are equal, the measurement of the angle, and that's by the definition of congruent angles. Knowing the measurement of angle 3 is 40 degrees, up here in the given, knowing that, we can substitute that 40 degrees right here for measurement of angle 3. That's also a version of the transitive property where we see that the measurement of angle 1, this statement here, and in the given statement here, we can apply the transitive property or the substitution property of equality to reach the statement we were trying to prove. Okay, another example, very similar. We know the measurement of one angle. We've got these congruent angles here where 1 is congruent to 3 and 3 is congruent to 4. Again, you can sort of see what happens. There's a slight twist to this proof where we'll see in just a second. We start with our given statements. We apply the transitive property of congruence here, so angle 1 is congruent to angle 4. We know that their measurements are equal by the definition of congruent angles. We know that the measurement of angle 1 is 63 degrees, so we can substitute based on this given statement. We can apply that substitution property to put 63 degrees in. But this statement is in a different form than our proof statement. So even though you might feel like we're finished with the proof, we haven't gotten our statement to look exactly like what we're trying to prove. So we're close, but we're not quite there yet. One more step, and that is to flip the two sides of the equation so that the measurement of angle 4 is equal to 63 degrees, and that's the symmetric property. Okay, one last example involving the transitive property, but now with an angle bisector. You see that ray AC bisects angle BAD. That's given. Based on angle bisecting, that tells us that the two angles that are formed by the bisector are obviously congruent by the definition. Whoops. That's the definition of the bisector. Angle 1 is congruent to angle 2. Now that we know that angle 1 is congruent to angle 2, given the given statement angle 1 is congruent to angle 3, one last step, and that's to apply the transitive property of congruence, and we've reached the statement we were trying to prove.